term, right? You need to find the general term first before you apply which test? Which test? Ratio test, exactly. So what is the general term? Well, what's one, let's say it wasn't, like sometimes you can look at these and just come up with the general term. What might you do to help you see the pattern? What's one thing you can, yeah, it's gonna be 0 factorial x to the 0 all over. Yeah, because how is 0 factorial defined? It is 1, exactly right. So if I were to write the general term here, oh, did I leave out a square? Thank you, that is important. Yes, definitely have a square there. Nice. So this is gonna be the summation from n equals 0 to infinity. What's gonna go on top? Well, it correlates kind of nicely, right? We don't have to move anything. What's it gonna be? Someone else wanna, Nozomi, you wanna tell me what it is? What's the general term gonna be? So we're running the ratio test. What's the limit we have to run? Limit as what goes to infinity? N goes to infinity of a n plus 1 over a sub n, like this. Okay, everybody get up, find a piece of the board. I want it out. Let's say f of x was equal to f of a plus this thing. What's another way to say f? What's another letter that is come to represent or in the past represented f prime of a? What? Exactly right. What about, oh, f of a could be with a y as the output, you know? So maybe, what is this? F of x minus f of a equals m times what? X minus a. So what does m equal? F of x minus f of a all over what? X, sorry, not m minus a, x minus a. What is that? Slope. So what this is, we've taken slope, we've gone backwards, and at this point, at step 2 right here, I'd call this step 2. You've seen that before. What is that called? We have a function. Yay, here's the true value of that function right here. Nice. See this, everybody? We have a point at x equals a. The height of that point is f of a. When we move over, we go over to x, we go up. What is this here? This distance right here is f prime of a times x minus a. This is x minus a. So what's the slope of this line? Oh, it's all right there. So could you write the equation of that line given that labeling? If you zoom in really far right here, if you zoom in really, really far right here, how close together are the tangent line and the slope? I'm sorry, the tangent line and the function. Not exact, but are they close? This is fun to do because you don't get to do this that often in math in the past. Either things are exact or they're not. In this case, there is a math word called neighborhood. In the neighborhood, in the area around this point, are they pretty similar? So for example, let's say this function was crazy complicated, but you were only interested in working with the numbers around x equals a. What could you use instead? Instead of using this function, you could use the what? The tangent line. There it is. There it is. You could use the tangent line. So you could use the tangent line to approximate this function around that point. What happens though as you march away from the x gets farther, the x value gets farther and farther away from a? What happens? What? Josh. What happens as you get further and further away from the a value?
The tangent line becomes a worse and worse approximation.
Exactly. That is not a linear function. So we have tangent lines. What else could we have? If we wanted to make this a little bit more accurate, we could have a tangent what? Yes? Now, instead of a tangent line, what could we have? Okay. What's 1 power up from line? 1 power up. There's lots of curves. Curves could have many different powers. What's 1 power up from linear? Tangent? Polynomial is any of those powers. Let's be more specific. Someone said it. Tangent what? Tangent quadratic. How did we find that again? How did we find a tangent line? We found the instantaneous rate of change at that point. We found the point and we used point slope form. Exactly. This is called the Taylor polynomial of degree 1 approximating f of x for x near 0. All this is saying right here, a tangent line is really good at approximating a function when you're really close to the value that it's tangent at. In this case, what's the x value that it's tangent at? What's the x value? 0. You'll get a choice sometimes where to nail these things to the function. When you can choose 0, 0 is nice. Okay, so let's take a look at this, for example. This one right here. Quadratic approximation, quadratic tangent. So P2 is going to be the second degree Taylor order polynomial. The second degree, meaning it's going to be a quadratic. Let's unpack this. To ensure that the quadratic is a good approximation, let's do it at cosine. we require that cosine x and the quadratic have the same value, the same slope, and the same second derivative. And the same second derivative at x equals 0. That is, we require all of these things to be true. All of these things to be true. So we need a function that we can differentiate to begin with here. We need to differentiate this function. So what's the first thing we have to have? Have the same value. They have the same value, the same slope, and the same second derivative at x equals 0. So what's the first thing we need to find? What is cosine of 0 going to be? Or what is cosine of 0? 1. Cosine of 0 is 1. So we know that this function has to pass, oh, you need to unfreeze it, sorry. Cosine of 0 is 1. We okay with that? What is the derivative of cosine? What is it? I heard a little discordance there. That wasn't totally harmonic. Negative sine of x? Do you agree that's negative sine? Derivative of cosine is negative sine? What's negative sine of 0? 0, we agree? Okay, we got a second there. And what about the derivative of negative sine? Negative what? Negative cosine of x, is that correct? Is everybody with me so far? We good? I'm just shaking this out here. Good. So we have the negative cosine of 0 is what? Negative 1. So we need a quadratic that satisfies all of these things. So first of all, we have at 0 it has to be 1. The first derivative at 0 has to be 0, and the second derivative at 0 has to be negative 1. On your own, try to take a guess, try to construct, tell me what this polynomial is going to be. Here are the facts. You have the information you need. Try writing it down on your own. Try writing it. So x, you said that a, because you knew that because this is negative 1, we pair that up there. So 2a has to be negative 1. So a is? Oh, thank you. Thank you. Is negative a half, like that. But then you also know that this one correlates to there. So what does that tell you? 0 equals 2 times negative a half, negative 2 times 0 plus b. So what does that mean b is? 0. Raise your hand if you've understood what we've done so far, where a and b come from. Raise your hand if you've understood it. The 0 came from, we know that the derivative, the first derivative at 0 of this is 0. These have to be equal by the highlighted, the same slope, the same second derivative. So this is the first derivative.
Yeah, I mean the 0 after.
Because at x equals 0. At x equals 0.
Oh.
At x equals 0 right there. Right? So then you do the same thing. You go up again. You go up again. Do I have another color here? Not really, but I'll do this right here. So what do we end up with here? We end up with 1 is equal to negative a half times 0 squared plus 0 times 0 plus c. What's c going to be then?
1.
C is 1. So what do we end up with for our polynomial? G of x is equal to negative 1/2 x squared plus what? Plus what?
0x.
0x plus,
C.
which is 1. So our final polynomial, written in its most simplified form, would be negative 1/2 x squared plus 1. So how could we visually check to see if this does what it says we think it does? Well, we could check it all. We could do everything in reverse, right? How could we visually see if this is, we could graph this. Graph both cosine x and that function on your calculator right now. Take out your calculator. If you don't have a calculator, sidle up to somebody who does have a calculator. Nozomi, where's your calculator? I like the smile. That was a good reaction there. Some people try to not make eye contact. You looked directly at me and smiled right there. That was good. I do have a stylus. There you go. This should work. I think I replaced the batteries recently. Graph both of them. I'm going to do the same thing. Graph both. You're not going to want to do that, right? You're not going to want to do that? So this is what we just did right here. Here's the general. I'm going to unfreeze it. Hey, look at that. I remember. Here's the general form right here. Here's what you just did. The coefficient of the quadratic was the second derivative at 0 over 2, the first derivative of 0 over 1. Oh, look at this. This is not written in descending order, but it gives you a hint of what we're looking at here. Does anybody want to guess what the next term would be if I made it to the third power? What's the if I wanted to go to degree 3, what would the next term be?
F to the third derivative.
F3 at 0 over what?
3.
Over 3?
Or 3 factorial times x.
Times x. So there's going to be x to the third, f triple prime at 0. Over what though? Be careful. So x, you see the 6, you can circle the 6 that you came up with right there in the triple prime. Where did that come from? The 6, you see that everybody sees where the 6 is? What did he start with? He started with g of x is equal ax cubed plus bx squared plus cx plus d. If I were to differentiate this once, what do I end up with? 3ax squared plus 2bx plus c. If I differentiate it again, what do I end up with? 3 times 2 times a times x plus 2 times 1 times b plus 0. What do you see? Factorial. If I started with, let's just generalize this. If I started with g, if I wanted to go g of x is x, let's say ax to the n, what happens when I differentiate? N-a-x to the n minus 1. And then what's next? N times n minus 1 x to the n minus 2. So if you did this out in completely generalized form, what are you going to end up with in your denominator? N factorial. N factorial. This right here is your friend. This is your friend right here. Stare at this. Let's just become one with this. This is awesome. This is fantastic. This is wonderful. What does this mean right here, by the way, when the n is in parentheses in the power? Not power. It's the nth derivative. Please don't run the power. Please, 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 please. That means the nth derivative. Yes.
Like, this is the last question, so like, I'm kind of confused because like our 2b should be actually a constant, right? Like 2b should be constant, but why yours is 2b?
Wait, Shema.
2. Like over here it would be like
Shema?
6ax plus 2b, and then it got like 6a plus 2. It should be just 6a.
That's probably correct.
Just 6a? Oh,
Yeah.
is there a mistake in there?
Well,
Yes. So we can. Is there a mistake? Is that are you being really nice?
Yeah, but no, I'm just confused because like they got quadratic, but if I do my way, I can't get anything.
Got it. Okay. I understand. So I know. I understand what you're asking. So you're asking is if you take the derivative of 2b, should you get 2 or should you get
I should get
0? Ah, you should get 0, right? So therefore, a is going to be
0.
So here's the thing. What's really awesome is that we actually have agreement for wrong answers. Or are they? My point is negative 1/3 here. So I got negative 1/3 right there. Did they make the same mistake right there?
Yeah.
Are you sure?
I think so.
You think so?
Yeah, they got 6a plus 2.
Oh, yeah.
Oh, look at that. So is there the same mistake right there? Is there the same mistake over there?
Yeah.
Is there the same mistake over there? I think so.
I can see that.
Yeah. No. Look at they have 6a though. So if you make one little tiny mistake, you end up with something that graphically, when they graphed it, did it look like it parallels it a little bit? It does look like it, right? Oh, okay, it doesn't though. Oh, yeah, you did. So let's take a look. Did you make the same mistake?
I don't think so. No, they're right.
What do you think?
They got the same.
Estimated to the 7th order Taylor polynomial, you would go until you hit 7 or go beyond it. And look what happens here. What happens to all of these terms? The even term, the even term, the even term. They cancel. So P7x, so the 7th degree Taylor order polynomial for cosine is this. If you graph this on your calculator, there it is, right there. That's really cool. That's kind of cool right there, right? What did we start with? Oh, actually, excuse me. What did this start with? This didn't start with cosine. What did this start with? This started with sine. So what would this be for cosine? We change it by one little thing. The even power. So if this right here is sine, if this is sine, what would cosine be? Hold on, one at a time. Let's go. Someone here. KU, what?
x2 over 2 factorial.
Hold on one sec. X2?
X to the 2 second power.
Does it start at x to the 2? It didn't start at 1, right? It started with 1, right? And then what's it going to be? What was the first? What's it going to be next? Minus what?
Minus x to the third power.
No, this is cosine, remember?
Sorry, second power.
Over
2 factorial.
plus
Plus x to the fourth power.
over
4 factorial.
minus
6 x to the 6.
over.
Factorial.
Oh, does this continue?
Yep.
Absolutely. So what's the difference here? Sine x minus, right here, 1 minus odds for sine. And look, see that right there? What do we have? Does that match what we have over in the bottom right? Look in the green over there. That was what we came up with originally, and what x came up with when you fixed it up right there. It's the same exact thing. What happens as you go to infinity? This becomes infinitely close to cosine everywhere. How would we know that this converges everywhere? We would run which test? The ratio test, and hopefully the radius of convergence would come out to be infinite. If the radius of convergence is infinite, then it converges everywhere. Exactly. Okay. I think we have just run